All right, so we're going to look at the review for our test and just kind of go over every topic that we've looked at so far, and just make sure we're feeling comfortable with everything before we take the test. So I'm going to go over the notes sections, and then you guys can try the ones that say now you try, and check your answers with the solutions posted on Schoology. So let's go ahead and get started. We started this unit with the central limit theorem. So the central limit theorem tells us that for a population of any distribution, so it does not have to start normal, it could be uniform, skewed right, skewed left, the distribution of the sample means approaches a normal distribution as the sample size increases. And some important things we figured out is our sample mean and our population mean are equal. So when we're calculating, our means do not change, but it's just our standard deviation that's going to change when we're calculating our normal distributions and trying to figure out our probabilities. So let's look at an example. So it says, engineers must consider the height of people when designing airplanes. American men have heights that are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. Sketch a picture or include the calculations used. Round the final answer to 4 decimal places. So if a male passenger is randomly selected, what is the probability he can fit through a doorway of 72 inches without bending over? So if we think about our normal curve and our mean is 69, and if our doorways are 72 inches tall, then anyone that's 72 or smaller or shorter would be able to fit through the doorway. So we're looking at this shaded region here. So if we want to find the population of people or the probability that this one person lives in that shaded region, we do our normal CDF. We go from our lower bound, which for us, since we're coming from this far end over here, is going to be -1 e to the 99. Our upper bound we shade all the way to 72. And then we do our mean and our standard deviation, right? The third number is always your mean. The last number is always our standard deviation. This is our upper bound. So we go ahead and put that in our calculator. To do that, we hit second vars. We go to number 2, which is our normal cumulative distribution. Our lower bound is -1 e to the 99. Our upper bound is 72, our mean is 69, and our standard deviation was 2.8. So then when we hit paste and calculate, we have that there's a probability that the one person that we select is 0.8580. So then we looked at if half of the 200 passengers are men, what is the probability that the mean height of 100 men is less than 72 inches? So this is where our central limit theorem comes in, right? We're going to consider that n is now 100 men instead of just 1. So again, that doesn't change our mean. However, it does change our standard deviation. So our picture is going to look exactly the same. We're still looking for everything shaded on the left part of our graph. And almost everything in our calculations will stay the same. Our lower bounds, our upper bounds, our mean, because our population mean and our sample mean is the same. The only thing that's going to change, my standard deviation will now be 2.8 divided by the square root of 100. Because I'm considering now 100 people instead of just 1. So when I do that on my calculator, I'm going to go ahead and just copy this down and then divide this by the square root of 100. And I get 1, which means that the probability is 1, meaning it's definitely for sure going to happen. Okay, so this would be a great time to pause the video and try number 3 and 4 before we move on to our next section. And the answers are posted on Schoology for you to check those. So I'm going to move on to our next topic, which was our confidence intervals. So a couple notes to remember about confidence intervals. The higher the confidence interval, the larger the range. So the bigger, right, the bigger the interval. So instead of a 90%, if we go to a 95%, the interval is going to have a larger range between the values. There's going to be more room, right, because we're being more confident that we have less errors. So we have to expand our range to make sure that we're finding the correct values. So if our confidence interval, let's just say, was X and Y, there are two values here, we'll just call X and Y. If we want to find the point estimate, that's our P with the little hat on top of it, our point estimate, or the center of the interval, we're just going to add up the two values and divide by 2. That will tell us the two values in the middle. And then to find the margin of error, once we find the number in the middle, we just calculate the distance between one of those edges, one of the ends of the interval. So if we look at an example, here are my two values. So to find the point estimate, I'm looking for the number in the middle. So I'm going to add up these two values and divide by 2. So when I do that, I have 0.735115 plus 0.8431. I end up with my point estimate being 0.7873. So the middle of this interval is 0.7873. So then if I want to find the margin of error, I have two options. I can take my point estimate and subtract the smaller part of the interval, or take the larger part of the interval, 0.8431, and subtract my point estimate. So we're just finding the distance, right? We know that this point estimate is right in the middle, so we're just finding the distance to either end of our interval. So if I find either of these, I would get that my margin of error is 0.0558. And I can just confirm that by finding the other distance, and I get the same thing. So my margin of error, right, we could write this as our point estimate, 0.7873, plus or minus our margin of error, which is 0.558. 0.0558. So again, giving you a chance, you can pause the video, try it for number 5, and check your answers. I'm going to go ahead and move on to the next section. So note that all of this stuff here will be provided for you on the test. So you're not expected to memorize any of these equations or formulas or the conditions. However, you should know how to use them. You need to know what they're used for and the purpose behind them. So if we look at our first kind of idea of, right, we're talking about our confidence intervals for a proportion. This is when we're given a percent or a proportion. We use our 1 prop Z intervals, right? I'm not going to tell you how to find it on your calculator. You need to be able to do that yourself. But I have my assumptions here for my proportions and any of the equations if I wanted to find them by hand as well. So the first thing before we do confidence intervals is we can figure out solving for the number of people we would need or the sample size. So for this one, there are 2 equations to solve for n. One of them is when we have a point estimate. One of them is when we don't. So if we look at this example number 6, how many people would you need to survey to estimate the proportion of people who own a cell phone but not a landline? Assume you want to be 95% confident that the sample percentage is within 4 percentage points of the true proportion percent. So it says, assume in a recent survey it suggests it's about 8%. So because this is kind of giving us, right, this is assuming that we're starting at 0.8, that's telling us that p hat is 0.08 when I turn that into a decimal. So because p is known, I'm going to go ahead and use this formula here. So n equals z star squared times p hat times q hat over e squared. So z is just our critical value based on whatever confidence level that we want. So since I want to be 95% confident, I'm going to use the critical value 1.96. My p-value is 0.08. Now remember, Q is just the 1 minus p. It's the probability that it's not happening. So if my probability of people is 0.8%, the probability of it not would be 0.92 if I was to subtract. So Q is 0.92. And then if I want to be within 4 percentage points, I am going to also turn this into a decimal, so 0.04 squared, right? 4% as a decimal is 0.04. So then when I calculate this, right, I'm just going to put that in my calculator. I'm going to do 1.96 squared times 0.08 times 0.92. So that's that top value, and I'm going to divide that answer by 0.04 squared. And I end up with 176.71. Now remember, we always have to round this up, because if I want an accurate answer and I need to ask 176.71 adults, I can't ask a decimal of an adult, so I have to do more than that, right? 176 is not enough, so I've got to round up to get to 177 adults in this case. All right, so then part B just says, assume you have no prior knowledge. That means that we don't have this p hat value or that point estimate. So we're going to go ahead and use this formula instead. So our z star value will still be the same. We're going to use 0.25 here in the place of p and q. And then our e will also be the same. So we're going to do 1.96 squared times 0.25 over 0.04 squared. So when I go ahead and calculate that, 1.96 squared, and then divide that by 0.04. Oops, that should be a 4. I get 600.25, which I will round up to 601 adults. Good. So on the next page is for you to try 7 and 8. So go ahead and try those. Again, checking your answer on Schoology, and then we'll move on to our next topic. All right, so our next topic is finding the confidence intervals ourselves. So again, we're still working with our proportion intervals. So we're still working with these notes here, using this information here for us. So we can keep that close by, especially for the conditions. So it says, in a recent survey of 102 random people, 701 said they voted in the recent election. Find a 99% confidence interval for the proportion of people who said they voted. So again, we're given a proportion here, 701 out of 1,002. So I know I'm going to do a 1 prop z interval. So for that, I need an n value. I know that n was 102. X is 701 because 701 people said that they participated. If I want to find p, remember that's just x divided by n. So 701 divided by 1,002 would give me basically 0.7. And then I want a confidence interval of 99%, so 0.99. So before we run our confidence interval, we always want to check our conditions. Again, remember your conditions are provided for you here in case you forget one of them. So the first one is that it's a simple random sample. It says that it asks random people, so we're going to check that condition. Our next one is that n times p is greater than 10. And n times 1 minus p is greater than 10. N times p is really just whatever your x value is. And if you want to confirm that, right, I can take my 1,002 times 0.7, and I get roughly 701. So this one is 701. That's definitely greater than or equal to 10. If I do n times 1 minus p, 1 minus 0.7, I end up with 300, which is also well above 10 to meet that condition. So then for our last condition, we just want to make sure our n size is reasonable. So if I take this and add a 0 to it, right, it is very reasonable to assume that there are more than 10,000 people that have a potential of voting. So we are good with our conditions, and we can go ahead and run our interval. So to run our interval, we hit stat, go over to test, and then we're running a 1 prop z interval, not test. So we're going to have to scroll down. For most of you, it should be letter A. And then we're just typing in the values that we have. So X is 701, N is 1002, and I want to be 99% confident. So I'll go ahead and calculate, which gives me 0.6623 and 0.73691. So then we always interpret our intervals the same way. I am, in this case, 99% confident that the interval 0.6623 to 0.73691 contains the true proportion of people who voted in the recent election. Remember, we're always wanting to include whatever our confidence interval was, whatever the interval we found, and then bring it back to how that relates to the problem that we're solving. We always want to make sure our answer, our interpretation is in context. So then this question asks, voting records show that 71% of eligible voters actually did vote. Are the survey results consistent with the actual voter turnout? So 71% is between our confidence interval. So yes, 71% is within our confidence interval. So our survey is consistent with the results. If for some reason the value was outside of it, we would say there must have been something wrong with our survey, maybe the people that we asked or something of that sort. But since that falls within our range, it looks like our survey was valid. Okay, so why don't you go ahead and if you turn the page, try number 10, which is another 1 prop z interval test for you to try. Again, pause the video, give this a shot, check your answers on Schoology, and then in a second we will move on to our t intervals. So moving on to our t intervals. Again, this information is given to you on your test in case you need it. Oh, also n. So this information is provided on your test for you. So you don't need to memorize these, but you do need to know what they're good for and how we can use them. So just like our other method, we can find sample sizes that we would need in order to create or come up with our proportion. So if we look at this, it says, suppose a certain species of bird has an average weight of 4.1 grams. Based on previous studies, we can assume that the weights of these birds have a normal distribution with a standard deviation of 0.36. Find the sample size necessary for a 95% confidence level with a maximum error of estimate of 0.18 for the mean weight of hummingbirds. So because we're talking about a t interval, we're using this equation to help us solve for n. So we have z star times our standard deviation over e, and then all of that is squared. So since I want to be 95% confident, that means z, my critical value, is 1.96. My standard deviation for this problem is 0.36. And then our error has nothing to do with a proportion or a percent. So in a t-interval problem, we just take the error for whatever it is. So in this case, our error is 0.18. But even if our error was a whole number, let's say it was 12, we would still just use the value 12 here. In a t-interval, we're not looking at a percents or proportions. We're just looking at the value of the number. So if I calculate this, I have 1.96 times 0.36 divided by 0.18, and then I'm going to square that value. So I end up with 15.36, which again, we have to round up in order to have enough data. So we're going to look at the mean weights of 16 hummingbirds in this problem. So try number 12 on the next page, and then we'll go ahead and look at doing our own t-interval. Okay, so if we want to practice running a t-interval, we'll look at example number 13. So it says a random survey of 48 first-year teachers in the U.S. found that their average monthly take-home income was $2,103 with a standard deviation of 220. Find the 95% confidence interval. So anytime we're given a mean and a standard deviation, that means we're running a t-interval. Again, we have the conditions for us, so we don't need to have them memorized, but we will have to check these three conditions. So we know that here that our n value is 48. Our mean is 2,103. Our standard deviation is 220. And then for our confidence interval, it is 0.95. So all the stuff we get from our problem. I want to do a simple random sample, which it says a random survey. So we'll say that condition's met. For a t-interval, this condition is just that n is greater than or equal to 30. So 48 is greater than or equal to 30, so that condition is met. Remember, if your n value is not greater than 30, if the problem says that your data is normally distributed, that also can check the box for condition number 2. If we look here, right, it says that n is greater than 30 or the population is known to be approximately normal. So if it says it's normally distributed, it's okay that if n is less than 30. And then if we look here that our n value is in a good size, if I put a 0 at the end of here, it is reasonable to assume that there are more than 480 first-year teachers in the United States on any given year. So we can go ahead and run our results. So we'll hit stat, go over to test. This time we're running a t-interval, which I believe is number 8 for most calculators. So then it asks us for, right, we want to be in stats because we have the data here. Our mean is 2,103. Our standard deviation is 220. N is 48, and I want to be 95% confident. So we put that information into our calculator and hit calculate. We end up with 2,039.1 to 2,166.9. So we can interpret those results just like we interpret all of our confidence intervals. I am 95% confident. Again, making sure you always talk about what percentage your confidence interval is based off of, what the interval is, and then what that means in terms of your problem. So the next couple questions, calculate the margin of error of a 95% confidence interval. So this is my 95% confidence interval. So to find our margin of error, first we need to know our point estimate. To do that, we can add up our two values and divide by 2. So if I take which is actually always going to be your sample mean or your mean. It is your mean with a margin of error attached to it. So then to find my margin of error, I take that value and I either subtract it from this or subtract this. So I can either do 2,103 minus the first part of my interval or the second part of my interval minus, and I would get the same value. So it's not really necessary to do both. Just pick one of them, and you're just finding the distance from the middle to one of the ends of your graph. So or one of the ends of your interval. So if I do that, I get 63.9. So my margin of error is 63.9. If I take this value and I add and subtract 63.9, it creates this confidence interval. So now it says find the sample size necessarily to cut the margin of error in half. So again, we're working with the t-interval. We now are looking for our sample size. So we're looking for n. So actually going to go back to that formula to help us solve for n. Remember it was n is z times our standard deviation divided by our error squared when we're working with the t-interval. So because I want to be 95% confident, that makes z, right? 95% confident makes z 0.95. No, it doesn't. I'm very sorry. It makes z 1.96. Let me just check that I'm correct on my table before we proceed, right? If I look here, 95, 1.96. Okay, now I know what I'm doing. So I have 1.96 times my standard deviation, which in this problem was 220, and then divided by my margin of error. Now I want to cut my margin of error in half. So instead of using E as 63.9, I want to divide that by 2 to figure out what the margin of error I actually want. So I get 31.95 here as my margin of error because I want half of the value that I had in the original problem. So 1.96 times 220 divided by 31.95, and then I'm going to square that. Says that my survey would have needed to talk to 182.14, which we're going to round up to 183 first-year teachers to cut my margin of error in half. So had my n size, right, my n size here was only 48. Had it been 183, it would have cut my margin of error in half. All right, so let's look at one more t-interval. If we look at number 14, we're solving the exact same things. It's just how we're given our data that's going to change in this problem. So as you can see, it doesn't tell us the mean and standard deviation. It just gives us a table of values. So there's kind of two options here. You can either type these into your calculator and find our mean and our standard deviation from our 1-bar stats. Or you can just have the calculator find it for you later. But I'll show you how to do both of them. So when we're given a table of values, we're still looking at a t-interval because we can find the mean and standard deviation of our table. So what I'm going to do is I'm going to go to list 1 and I'm going to type in all of my values that I have. I'm going to type in all these values into list 1, and I'm going to be very careful to make sure I don't mess up because that will change all of my numbers if I do. And you should be doing this and practicing this skill alongside me. Okay, so I have all of my data typed into my calculator into list 1. So the first option is, if you want to know the mean and standard deviation before you get started, you can totally find that. We did this in Unit 2. If you hit Stat, go over to Calc, pick your 1var stats. You're telling it to take it out of list 1. So I'm taking it out of list 1. And so I get a mean of 314.84. And S of X is my standard deviation, so 42.13. So we can do it this way, and then we can run everything else as normal. Let's check our conditions before we go ahead and run our confidence interval. So first, is this a simple random sample? We're going to assume yes. Then it wants to know if n is greater than or equal to 30. In this case, it is not. However, it says that the production process is normally distributed. So even though n is not greater than or equal to 30, it is normally distributed. So we can go ahead and still check this condition and move on. And then if we want to check that our sample size is appropriate, we have 20. It's safe to say that they probably have more than 200 of these things going out, or of these rods, tension wires going out at a time. So if I want to run my t interval, I go stats over to test down to t interval. I can use stats and type in the numbers that I found, right? Or I can go over to data and just tell it pick from list 1. List 1 is where I put all of my data, and then I want to be 90% confident. When I calculate that, it's also going to tell me here what my mean and my standard deviation are, and it should match what I found using 1var stats. So it's really, there's not a right, wrong way to do this. It would just be easier just to let the calculator find it for you, but I know that sometimes we feel more confident if we know that going into typing in our interval. So, doesn't quite matter, but I get my confidence interval to be 298.55 to 331.13. So then I can go ahead and interpret my results. Okay. So then it says the manufacturer reports the average temperature reading should be 295. Based on the data, is there reason to believe that the machine is not working properly? So we would look, is 295 within our interval? It is not. So then therefore, either something is wrong with our sample or something is wrong with our machine. So we're going to assume, based on our data, if we did everything right, we ran a simple random sample, that our data is valid. I would say yes, because 295 does not fall within our interval. It is safe to assume the machine is not working properly. Okay, so then from there, the last couple ones are t interval examples. So go ahead and give those a shot so that you can keep practicing. And again, check your answers on Schoology just to make sure you're on the right page before your test next class. But hopefully this review kind of helped you see the types of questions you should be seeing on your test.